Hello everyone. In this video, I'm going to talk about gradient descent backpropagation algorithms which are used in neural network training. Let's get started with some basic calculus. Calculus. Let us suppose we have a function f of x is equal to 3x squared and we do not denote the output of this function with the output variable y. That is y is equal to f of x is equal to 3x squared. If we draw the function in a 2D plane, it will take shape something like this: x-axis, y-axis, and it will take the shape of something like this. Now here, like, we have to find out the derivative of that function, derivative or slope of that function at any particular point. So it is denoted by dy by dx, and by definition slope or the derivative of it is limit h tends to 0 f of x plus h minus f of x divided by x plus h minus x. In this example, it is 3x plus h whole square minus 3x square divided by x plus h minus x. These two terms cancel out, and 3x square 6xh plus 3h square minus 3x square divided by h. These two terms cancel out, this cancels out, and this get cancelled out. We are left with 6x plus 3h. Since h tends to 0 and h is a very small number, this 3h term also is a small number. We can ignore that and we are left with 6x. So this is the formula. This is the formula to calculate the slope or the derivative of that function. Suppose we want to evaluate the slope of it at a particular point. Let us say dy by dx at point x is equal to 2. We just substitute the value of x in this, that equal to 12 here. Similarly, we want to find out the slope at x is equal to minus 2. We substitute the value in this, like we'll get minus 12 here. So the derivative at that particular point, what that actually means is, if we draw a tangent to the curve at that particular point, the slope of the tangent is equal to for example, in this case, the slope of this tangent at x is equal to 2 will be 12. Okay, now let's move on to other concept. Now for this curve, we have to find minimum value. We have to find the value of x at which y is minimum. Find value of x at which y is minimum. In other words, like, we have to find something like x star, where it is the argmin of function of x at x. So we have to find out the value of x at which the value of y takes the minimum value. And from this diagram, like, we can say the value of y is minimum at point x is equal to 0. From calculus, what we can say is y takes the minimum value where dy by dx is equal to 0, where the slope of the curve at that point is equal to 0. So in this example, it is 6x equal to 0, that is x is equal to 0. So at x is equal to 0, we can get the minimum value of y, or y takes the minimum value at x is equal to 0. This is from the calculus, and we take the first derivative of it and we make it equal to 0, and at that point the function y takes the minimum value. So this is one way of finding argmin of x, or finding the value of x at which y is minimum. So there is other method that is called gradient descent. And let's discuss about the gradient descent now. I'll redraw the curve here again. This is x, this is y, 0, 1, 2, say minus 1, minus 2. Suppose we have found out the value of y at x is equal to 2. At x is equal to 2, we find the value of y. We have got some value of y over here. Now we need to decrease the value of y in order to minimize the value of y. So we are at this point, we need to decrease the value of y. We can decrease the value of y by changing the value of the variable, that is x, the input variable, that is x. So now we have to find out, to decrease the value of y, whether we should increase the value of x here or decrease the value of x here. When we are at point x is equal to 2, we have to decrease the value of x in order to reduce the value of y, so that like it can move towards minimum. Similarly, let us say we have evaluated the value of this function at x equal to minus 2, at x equal to minus 2. So at x is equal to minus 2, let's say we have got the value of y, something over here. Now we have to reduce the value of y. So to reduce the value of y, whether we should increase the value of x or decrease the value of x at x equal to minus 2. From this picture we can see that when we are at x is equal to minus 2, we have to increase the value of x in order to reduce the value of y. And let us see what are the derivatives of it at x is equal to 2 and x is equal to minus 2. At x is equal to 2, the derivative is like plus 12, and x is equal to minus 2, the derivative value is like minus 12. That means the derivative or the slope of it. That means when the slope of the curve at that point is positive, we have to decrease the value of x. When the slope of the curve is negative, we have to increase the value of x. So that's the whole idea of gradient descent. So the algorithm, just a moment, I'll erase and make it little clear. Okay, this is the curve. So that's the whole idea of gradient descent. We start at any random point on the curve, and we want to know in which direction we should move in order to move towards the minimum value of y. So that is given by the first derivative or the slope of the curve at that point. And the algorithm is like this: x new equal to x old minus alpha into dy by dx. So here alpha is the step size, and this is the first order derivative of the function. So let us say like we are at value x is equal to 2. We initialize the value, that is x is equal to 2, and we step, let us say the step size is like 0.01 here, and we evaluate the derivative or the slope of the curve at that point. Here at x is equal to 2, the slope of the curve is like 12, and we move towards, we kind of decrease the value of x in order to move towards the minimum. So here it is like 1 point. We get the value as like 1.8. Again at 1.88, we find out the first order derivative of the curve again at 1.88, and again we update the value of x, and we move to a new point again, and again from that new point we again apply this formula, and then like we slowly move towards the minimum. So repeat this algorithm till the value of x new and x old doesn't change, and eventually it will converge to the minimal value, because at the minimal value x is equal to 0, dy by dx is equal to 0, so there won't be any changes in the old and new values, and it will converge to the value of y. It will converge to the point where the value of y is minimum. So this is like a case of single variable function. Even in terms of multivariable function, the concept remains same. Let us say we have a function y in terms of two variables, that is x1 and x2, that is 3x1 square, let us say 4x2 square. This is one of the sample multivariable function. If we draw it in 3 dimension, it can take a shape something like this. Let us say this is x1, x2, and this is y, and the shape of this function will take something like this. So in case of multivariable function, we calculate the partial derivatives. Partial derivative is nothing but we treat the other variable, all other variables as constant, and we evaluate we find out the slope at a single variable. So we find this is like partial derivative, and the vector of partial derivatives is called gradient. That's why the name gradient descent. And for this function, the set of partial derivatives will be like dy by dx is equal to 6x1, dy by dx2 is equal to 8x2. So in case of multivariable functions, the algorithm, the gradient descent algorithm will be as follows. We have x1 new equal to x1 old minus alpha into dy by, this is like the partial derivative of the function with respect to x1, and x2 old minus alpha, that is dy by dx2. And we keep updating the variables until it converges. Suppose here on this plane, like we start at a particular point. This is a particular point. We have initialized the values of x1 and x2 at this particular point. Now here should we increase the should we decrease the value of x? Should we decrease the value of x or increase the value of x? 1 minute. Should we decrease the value of x or x1, or should we increase the value of x1 or x2? Similarly, x2 we have to increase or decrease. Like this, we can find out by calculating the partial derivative of the function at this particular point. Once we have a partial derivative, we apply this update rule to both the variables, and we apply this update rules to the both the variables, and we keep descending. That's why the name gradient descent. We keep descending, and eventually like we will go to the minimal value. So this is about gradient descent when there are multiple variables involved. So ideally, so what gradient descent does is like, we have a function. We need to find out the value of x at which y is minimum. So one straight way is like find the first order derivative and make it equal to zero. The other way is like the gradient descent. Gradient descent, the crux of the algorithm is we initialize some random value and we calculate the gradient, and we keep decreasing the value of the variables in the negative direction of the gradient at that point, and eventually we will we will converge to the point where the value of y is minimum. Yeah. Now let's talk about neural networks. So you must be knowing the neural network has something like different layers, and each layer has nodes, and the nodes are like connected um, to the other nodes, something like this, something like this. And we have input values or the input vector. Say let's denote it as x1, x2, x3, x4, and we have weights w1, w2, w3, w4, etc. Similarly, something like this, we have set of weights and input values. And to predict the value of y predict, it is a function of weights and the input values. And we have a loss function, something like this. This is the difference between the predicted value and the true value, the square difference between predicted value and true value. It will take a form something like this. And if we see the loss function is a function in terms of w weights, input values or the input vector, and the true value of y. If we see for this function, these are all the variables, meaning we can change these, and we can change this. And x1, x2, and y are the constant. This is the input vector or the input data, and we cannot change it. Now this is the loss function. We need to find out the minimum value of the loss, or we need to find minimum value of this loss function. We need to find out the set of variables, set of weights where this loss function takes the minimum value. And if you see, this is like similar to this function what we have discussed, y is equal to f of x is equal to 3x square. But here the target function is the loss function, and the variables are like w1, w2, wn, and we need to find out the minimum value for the loss function, and we need to find out the set of parameter at which the loss function is minimum. So for this, like it is like applying the gradient descent. So we make use of gradient descent. So we find out the partial derivative of the loss function with respect to each of the weights, and we keep updating those weights, and eventually we arrive at set of weights at which the loss is minimum. At which the loss is minimum. But there is one problem. Finding out this partial derivative of the loss with respect to each of the variables, it is not a straightforward thing, because if you take the neural network function, which is in terms of weights and input variables, it can be a very complex function, something like this is a sigmoid function in terms of weight, and then another sigmoid with respect to another, and and something like this. The neural network has layers and layers of different layers, and each layer has a non-linearity. There are many weights, many variables involved, and efficiently finding the partial derivative with respect to each of the individual weight is like not a straightforward. Here one of the non-linear function or the sigmoid function is of type 1 by 1 plus e to the power of minus 6. So you can see like this is a the neural networks is like a complex function, and finding the partial derivative is not a straightforward thing. So the question is, how do we efficiently find out the partial derivatives and then like plug into this gradient descent equation, and then like we can arrive at a set of weights where the loss is minimum. So for that we have back propagation algorithm. So the whole idea of back propagation is, let us say we have a function y is equal to f of w1, or in terms of w1 and w2, let's say 3w1 and 4w2 plus 5. So we take any function, whether simple or complex, and create a computation graph for those functions. So the computation graph, it looks something like this. So so this is like a multiplication node, and this is like a plus node, and we have the output value y. So the computation graph is, we create a computation graph something like this. The whole idea is like we take any simple or complex function, and we express it in terms of simple and manageable units by creating a computation graph. In this computation graph, one simple manageable unit is like something like this. We have a node, and this node has like inputs, and it has like one output. So once we have a computation graph which is in terms of these simpler units, we do a forward pass. And we evaluate the value of y, and we do a backward pass, and we calculate the partial derivatives of the target function with respect to any of these variables. So forward pass must be straightforward. We just substitute the values, and then the output of one particular node becomes the input, and we keep propagating toward forward, and we arrive at a final value of y. The backward pass is also something similar. Initially, we start with dy by dy, and if you look at the manageable unit, the simple manageable unit, this manageable unit has something called a incoming gradient, and it has something local gradient, and it has something called as outgoing gradients. So let us denote it this like x1, x2, and this is z. So the incoming gradient will be something like loss by z, and so we have something called as incoming gradients. These incoming gradients, we take those incoming gradients and we multiply it with the local gradient, and we arrive at the outgoing gradients. These outgoing gradients will form an input to other nodes in the computation graph. So that's a whole idea. We construct a computational graph. We take any complex function, express it in terms of a simpler manageable units by creating a computation graph. And once we have this computation graph, we look at the individual small manageable units, and while doing the back propagation, we have the incoming gradients, we have the local gradients, and we calculate the outgoing gradients. And in this way we will efficiently compute the partial derivative of a loss function with respect to any variable with a single backward pass, and we start off with for this entire computation graph, the initial incoming gradient will be something like dy by dy, or loss by loss, that is like 1. We start off with that, and we back propagate, and then like in one single pass, like we can calculate the partial derivative of the loss function effectively, and then once we have the partial derivatives of the loss function with respect to any of the variable, we plug into this equation, and we keep updating the weights, and we arrive at a set of weights where the loss is minimum. So that's all. So that's all on the back propagation and the gradient descent algorithm. In a neural network, we initialize the weights with some random values, and at each of those random weights, we calculate the gradients, and we keep updating the weights of the neural network, and eventually we will arrive at a place where the loss is minimum. And the gradient descent and the back propagation algorithm tells, if we are at any random point in the network, any random point in the network, it will let us know whether we should increase the variables, we should increase the variables, or we should decrease the variables. So that is like determined by gradient descent and the back propagation algorithm. That's all. Hope you enjoyed the video, and thanks for watching the video. Thank you.